Hi, this is Binner. I'm a senior application engineer at Bentley Systems. Nowadays, we are receiving more questions about how to consider the deflection of floating structures during hydrodynamic calculation and also during time domain simulations. So, this webinar is aimed to answer these questions. Let me start. Here's today's content. First, for those of you who are not familiar with this topic, let me give you a brief introduction about hydroelastic analysis and why and when we need it. Then explain the methodology of the analysis and how to implement it in Moses. Let me move on to this introduction part. First, hydroelastic analysis is the analysis which considers the elastic deformations of floating structures when calculating fluid forces and resulting hydrodynamic reactions, the radiations. To be specific, famous researcher and also Professor Parkinson says that it is the study of marine structures when mutual interactions of fluid flow and the structural elastic reactions must be considered simultaneously. So here, all of them says that structural and hydrodynamic characteristics should communicate each other. Here the question is that, do we always need to consider the elastic deformation for hydrodynamic calculation? Let's briefly talk about when we need this type of analysis in the next slide. Usually, when the size of body is relatively small, it shows the rigid body motion against external forces. Just push the one part and it just rotate. However, as the size of the floater becomes larger, it shows the local deformation against the external forces. In other words, local elastic response becomes dominant when the floater becomes relatively large. As for this relative size of floaters for elastic response, Japanese researcher Suzuki and Yoshida suggest formula to calculate this characteristic length, lambda c. This length indicates the influence of applied load on elastic deformation. So, if this characteristic length is longer than the wavelength, global response becomes significant. But if it is shorter than the wavelength, we need to catch the elastic response when calculating hydrodynamic forces. This means we need to consider the elastic response when analyzing these kind of very large floating structures. Here, floating airports, bridges, cities, and some oil and gas terminals. These are the structures where characteristic length is larger than the wavelengths. So in this regard, characteristic length could be the definition of the very large floating structures, in a mechanical sense, and could be the criteria about when we need the elasticity for hydrodynamic computation. So far, we will talk about the definition of the hydroelastic analysis and when we need it. Now let's talk about the methodology. This is the definition of the hydroelastic analysis we saw in the previous slide. Here, for the body deformation, we need a structural analysis solver. I just write it as a finite element method solver. This is to form a mass and stiffness matrix, also force vectors, and solve for displacement. And also for the hydrodynamic computation, we need to have a boundary element method solver. And we model the physical boundaries that represented by panels and solve for the problems for potentials. And also, for hydrodynamic pressure calculation, we need to employ the boundary element method. For this, we model the floating structures with panels and solve the boundary value problems for potentials to get hydrodynamic pressures and some coefficient. As we talked, in the hydroelastic analysis, these two solvers should communicate to each other. Let me explain what each solver does. First, as for the structural part, the analysis employs the structural dynamics technique to calculate body deformations. This structural dynamics techniques assumes that deformations of a body can be represented by a set of displaced shapes. This assumed displacement is called generalized displacement, or displayed modes, or more generally, mode shapes. Let me take an example. We are familiar with motion areas of floating structures. Here, we assume area for each degrees of freedom represent the displacement for that degrees of freedom. In other words, surge area represents the displacement of the entire body in longitudinal direction. This is a kind of mode shape, and entire displacement of the body is a superposition of the areas for each direction. Let me give you some more detail in the next slide. Structural engineers use this undamped dynamic equation without external forces. And as we talked right before, the engineers assumes that displacement can be represented by assumed displacement and some time variant term. Displacement varies in time and space. They split this in time and spatial variant term here. Then after some operation, the solution of this equation becomes the determinant of this matrix. Then, by solving this equation, what you get is a set of natural frequencies and assumed displacement, which is corresponding to each natural frequency. Then, using the orthogonality of the matrix of the mode shape, assumed displacement, we can get a set of uncoupled equations in the generalized coordinates. These mass, damping, stiffness, and forces in the generalized space will communicate with the result from boundary elementary solver. For your reference, this is what generalized degrees of freedom module of Moses does. As regards the hydrodynamic computation, here is the general procedure for the boundary element method. First, we need a set of boundary conditions such as at the water surface or seabed, and also at the boundary of the floaters represented by panels. We can solve the boundary value problem with Green's functions for potentials. And from the potentials here, pi I in potentials of the induced wave, deflection, and radiation potentials. This pi is not the mode shape. This is a potentials. We get from these potentials, we get added mass and wave damping and linear exciting forces acting on the submerged parts of the panel. The pressures on panels are mapped onto the structural nodes for structural analysis. This is general hydrodynamic analysis procedure with potential theory. Once we finish the eigen analysis with the structural solver and this hydrodynamic analysis with the hydrodynamic solver, next step is to connect them together. Those hydrodynamic and structural properties are plugged into the motion equation. Then establish the uncoupled equations for each vibrating mode using the mode shape we calculated in the structural solver. As you see, hydrodynamic mass, added mass, fluid mass here, and the fluid damping and hydrostatic stiffness are all plugged into the motion equation. For your reference, this is a motion equation in the frequency domain. Also, here, structural mass of the structural element, and the structural damping, usually input directly to the software, and then stiffness of the structural element are also plugged into the same equation. Then, using the orthogonality of mode, we get uncoupled equations with generalized mass, damping, stiffness, and also forces. Here, linear superposition of the displacement and the forces will be used for all the computations such as motion analysis or time domain simulation, etc. This is called hydroelastic analysis through the modal expansion method. And this is what Moses does for hydroelastic analysis. After this modal computation in Moses, all the frequency domain, time domain, and even static analysis for the equilibrium position considers the deformation inertia through these modal superposition techniques. This is the end of the theoretical part, and let me explain how to implement this hydroelastic analysis in Moses.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.